I get to have this opportunity because of the special collaboration between Town Hall and the University of Washington's Engage program. Together they host a series called the UW Science Now as a part of the Seattle Science Lectures. Sponsors include Microsoft and KPLU. Each speaker's program will run about 25 minutes, which includes 5 minutes for your questions. We ask that you come to the mics on the edge of the stage so they can be included in our recordings. Before I introduce our first guest, though, I'd like to mention some other events from our science series. First of all, please join us tonight for Hope Jarin, who will discuss the benefits of a career in science tonight at 7:30, following these Engage talks. Also, I will be giving the next talk in the UW Science Now speaker series right here on May 6th, starting at 6 p.m. I will present on the ocean's most interesting weather features and their impacts on marine life. And now for our first guest. For the general public, plankton is one of the most overlooked life forms in the ocean. For University of Washington PhD student Elisa Bonnin from the School of Oceanography, they're the most fascinating. She'll share her research on climate change and what paleoproxies, including foraminifera, can tell us about how our planet has changed in the past and what to expect for the future. Please give a warm welcome to Elisa Bonnin. Elisa.
So today I'm going to talk about climate change, and yes, I'm going to talk about plankton at some point. But before I get to climate change or plankton, I want to talk a little bit about who I am and where I came from, because it's going to come up a little later in the talk. So I'm from this country called the Philippines, which is in Southeast Asia, a little bit north of Malaysia and Indonesia, near Thailand and Cambodia. And as you can see, it's an island country. It's made up of about 7,107 islands, give or take, depending on the tide. That's not a joke, we lose some. I grew up here in the province of Negros Occidental, in the middle of the country. My hometown was called Bacolod City, which is where the Star is located. And then when I was 16, we packed up and we moved all the way to rural South Carolina. So from the capital of a province in the Philippines to a town of about 8,000 people. So it was a big change. I did my undergrad at the University of South Carolina, where I studied chemistry and marine science, and then moved on to the University of Washington in Seattle, where I'm currently pursuing a PhD in oceanography. I decided to study climate change because it's a fascinating subject. And by the way, this is me in my lab when I defended my master's in February. And so we're working on climate change and how we study it. And I started working on that problem because it's fascinating and really interesting to me. And it's a relevant problem that's going to affect the world today. But the climate change and the way I viewed it really started to take a personal turn in my first year of graduate school, when something happened that sort of made me reevaluate how I think about climate change and what it means for human life. This is a picture of a storm called Typhoon Haiyan, or we called it Super Typhoon Yolanda in the Philippines. It was the strongest typhoon, at the time it was the strongest typhoon to make landfall. It hit the Philippines in November of 2013, so this is a weather map image of the storm. And just for reference, this is my hometown, right here in the star. So we were actually in the path of this storm. We survived. We didn't take the brunt of the damage, but we still took quite a bit of damage from the storm. This storm caused about $3 billion in damage when it hit. It displaced 4.1 million people and destroyed and damaged 1.2 million homes, of which over half were destroyed. The government estimates that 6,000 people died from this storm, but the actual death toll may be higher, and 1,000 people are still missing. So that's a lot of damage in a country where 2 out of 5 people live on less than $2 a day. The storm surges from the storm, that's the water that gets pushed in by the storm, rose as high as 5 to 6 meters, so that's about 20 feet. So just imagine a 20-foot ocean wave coming down on you from the storm. That's a picture of a house right there getting destroyed. And this is the city of Tacloban in Leyte, where the storm made landfall before and after the storm hit. So this storm actually caused a lot of damage that people are still recovering from today. And while we can't conclusively say that Typhoon Haiyan happened because of climate change, we can say that because the Earth is warming, storms like Haiyan are probably going to become more frequent in the future because storms take their energy from warmer water. So before, I'm going to go over a little bit about how climate change happens and what climate change is. Most of you have heard about the greenhouse effect. So basically what this is that as the sun sends heat towards Earth and it strikes the Earth's surface, some of that heat gets reflected back out into space. And the reason that we don't lose heat, the reason that we are able to keep heat at night even when the sun isn't directly hitting us, is because we have this layer of carbon dioxide, which we call CO2, in our atmosphere. So this CO2 acts kind of like a blanket that covers the Earth. And what we've actually been doing is, since the Industrial Revolution, we've been pumping more CO2 into the atmosphere through the burning of coal, oil, and other fossil fuels. And so we've been actually making that blanket thicker. We've been increasing the atmosphere's ability to we've been increasing the Earth's ability to retain heat. And so if you pay attention to this plot here, on the bottom you have time since the Industrial Revolution. So this caps out at about 2010. On the right-hand side of the graph, you have carbon dioxide in parts per million, which is just a unit that we use to measure carbon dioxide. On the left, you have the change in temperature in degrees Fahrenheit. And this blue curve here is global temperature, and this red curve is carbon dioxide. And as you can see, since the Industrial Revolution, carbon dioxide in the atmosphere has been increasing, and temperature has been pretty closely following this plot, or the carbon dioxide line. And this isn't a new phenomenon. Carbon dioxide and temperature have been going together for centuries. This is just the same plot, but expanded out to 400,000 years before present. And on the left-hand side, you still have temperature change. On the right side, you have carbon dioxide, except now carbon dioxide is in blue and temperature is in red. As you can see, throughout Earth's history, carbon dioxide and temperature have been cycling in this very natural way and have been going hand in hand. But if you pay attention to the right side of the graph right here, this little uptick is today's carbon dioxide increase, which has been leading to an increase in temperature. And so actually, pre-industrial carbon dioxide capped out at around 280 parts per million, whereas today we've hit and passed 400 parts per million already, and that number is continuing to climb. So some of the other effects of climate change, besides general warming of the Earth's ocean, sea level will rise because as the ice caps melt in Greenland and Antarctica, that's going to put more water in the ocean and cause an overall change in the Earth's sea level. And also, since when things warm up, they expand, and when they cool down, they contract. As the Earth's temperature increases, the water is actually going to expand, and this is going to cause some sea level rise. And that's actually what's causing most of the sea level rise that we're observing today. Rain levels are probably going to change all over the world as certain parts of the Earth warm faster than others. So some parts of the Earth may get wetter, and some parts, like California, may get drier. Storm intensity and range are probably going to increase, since storms like Haiyan and hurricanes like Katrina take their energy from warm water. So when the warmer the water is, the stronger the storm is likely to be. And also, and this is especially a problem for places like the Pacific Northwest, as the amount of carbon dioxide in the atmosphere increases, it ends up in the ocean, dissolving in the ocean, and that actually increases the acidity of the ocean. Sort of for the same reasons that carbonated beverages like Coca-Cola and Pepsi are acidic. And this is a problem for creatures that make their shells, like mussels, corals, oysters, and these little snails here, which are called pteropods, and these are actually things that salmon eat when they go out into the ocean, and they're negatively affected by ocean acidification. So a little closer to home, here are some of the climate impacts that we're looking at for this region. The overall amount of rain we'll be getting isn't going to change much, but because it's going to be warmer overall, that means more of it will fall as rain in the winter, and so there will be less snowpack. And because summers are going to be warm and dry, we're probably going to have more summer fires, like the fire that happened in Okanogan last summer. Because there's going to be less snow, we're projecting a decrease in summer river volume, which is going to be a problem for the water supply of the city going on into the summer, and also for power, because 70% of the power in this area is actually hydroelectric. We're projecting to see sea level rise, and as I've mentioned, ocean acidification is going to hit this area especially hard, and is already hitting this area today just because of how the ocean moves and works. And moving back to where I came from, some of the impacts that we're expecting to see in the Philippines, we're also expecting to see sea level rise, which is going to hit us hard because we're an island nation, and so we don't have that much land to move to as the sea starts coming in. We're going to see an increase in rainfall, which is likely going to lead to an increase in landslides. We're going to see increasing storm intensity, so more storms like the one I showed you in the beginning. We're probably going to have a decrease in rice yield as temperatures go up, and this is a problem because for many Filipinos, rice is a staple food. Mosquitoes and other pests like warm, wet conditions, so it's very likely that we're going to see an increase in pests and disease. And also we're going to see fish migration to cooler, inaccessible waters, and so most people in the Philippines also get their protein from fish. And because traditional ways of living like farming and fishing are going to be less viable, we're actually projecting to see an increase in urban migration as people pack up and move to the cities to try and find work, which is probably going to lead to more people living in slums. So all of these things are very bad, and as scientists we want to figure out how we can solve these issues, but also exactly what those issues are going to be. And a lot of the problems with understanding climate change is that we're here, we're in the present, we can only see a very limited amount of time. There hasn't been that much time in Earth's history that humans have been around taking notes and measurements, and that we've been able to see climate changes. If you take the whole history of the universe and condense it down to one calendar year, where the Big Bang happens on January 1 at midnight, the entirety of recorded human history can be fit into the last 15 seconds before midnight on December 31st. So actually a lot of things have happened in the past that we don't know about, and if we want to figure out the future, well, maybe we can look back in the past and figure out how Earth's climate has changed in the past. And from understanding that, we can look at how climate changes into the future. And one of the ways, or the way that we understand how climate has changed in the past, we're using these things called proxies. So to help you understand what I mean by proxies, I'm going to tell you guys a story. Imagine that you're a prisoner, you're locked in a cell that has no window. You can't see the outside at all. So you can't see the sun, you have no idea what the weather's like. The only people you see each day are the guards that pass by your cell to give you food and to check on you and make sure you're still there. How can you figure out what the weather's like outside if you can't actually see it? Well, you can look at the guards. You can see what's on their clothes as they walk in. If their clothes are wet, then maybe you can assume it was raining outside. If they're sweating, it's hot. If there's dust on them, maybe it's dry and dusty out there. If there's mud on their shoes, maybe the ground is wet. And so all of those things, water on the guards' clothes, dust on their shoes, those are proxies for the weather. You can't actually see the weather, but you can see the guards, and so you're using this information that you have to tell you something about what you can't see. And so all of us are kind of like that prisoner. We have no idea what happened during that long stretch of Earth's history that we weren't there for, but we can look back and see things that were there. And we can actually go back and analyze those and figure out how they must have come about, and from there infer what the climate must have been like and what sort of changes happened in the past. So here are some of the ways that people do that. One of the coolest, pun not intended, ways that people look at the past is through the use of ice cores. So these are ice sheets. This is a picture of the ice sheet up in Greenland, and this picture is the ice sheet in Antarctica. And so this ice has actually been building up for hundreds of thousands of years. And what people actually do is they take cores of this ice, so they just take out big chunks of it, and they can actually find fossilized air locked up in that ice, and they can analyze it and actually get direct CO2 measurements. And they can also figure out temperature just based on the way that the oxygen in water works. So this is very awesome, and ice cores are actually one of the best ways to figure out a lot of things about the past. But if you've noticed, they have a very limited geographical range. They really only tell you, they're a good approximation for global temperature, but they don't really tell you specific things outside of what's happening in the poles. So we want to figure out what's happening in the rest of the world where most people live. And people also can look at fossils. So these are actual plants or animals that have been trapped in rock and are pretty well preserved. And they can look back at those, analyze those, and figure out what the temperature is like, or what other aspects of climate were like in the past. And also people can actually look at the chemical information locked up in rocks, so how the rocks formed, how certain elements are incorporated into rocks can actually tell you a lot about climate. And this is all on land. However, one of my favorite ways to look at the past, and as some of you may have guessed from the introduction, you can also look at this species of plankton, or this type of plankton, which are called foraminifera. I call them forams for short, most people do. And these guys are plankton that live in the upper ocean. They actually live all over the ocean, but the ones I specifically am interested in live in the upper ocean, near the surface. And they have these nice, beautiful spines when they're alive. And when they die, they cast off all their spines and become these really nice white shells. And so how foraminifera can tell you about climate has to do sort of with how they live and form their shells. So this is just a schematic of the ocean. And if you have your little happy foram here, as it's living and forming its shell, it makes its shell out of calcite, which is a calcium carbonate material that's sort of like limestone. And as it's making its shell, it's taking in mostly calcium and carbonate from the ocean, but it's also taking in all sorts of other elements like magnesium, oxygen, sodium, boron, all sorts of impurities. And actually, we found out that the level or the amount of those impurities in these shells actually relates back to different properties of climate. So you can actually take these shells and analyze them and figure out a lot about what the conditions were like when this organism was alive. And thankfully, because its shell is made up of this hard material, when it dies, the shell sinks down to the sediments, and you can actually go back and dig that up, and if you can figure out what time period it corresponds to and have an intact specimen that you can analyze, you can figure out a lot about Earth's history. And one of my favorite proxies that I use with forams is actually related to the magnesium. So the amount of magnesium in their shell is a very good measure. It's a very good way of looking at what temperature was like. And since these guys live near the upper ocean, figuring out ocean temperature at that time period is a very good way to then figure out what climate must have been doing. And so this is just an example. This is a complicated graph, but bear with me here. This is just an example of how we use this proxy in real life. So this is one of the first studies that ever used this proxy to apply to a real life problem. And on the bottom you have temperature measurements. The bottom plot is temperature measurements from ice cores, so those nice cores I showed you earlier. And on the top you actually have the amount of magnesium. It's relative to calcium, but it's basically just the amount of magnesium in foram shells. And as you can see, those plots line up fairly nicely. And this was actually the paper that proved that this could be done, that foram magnesium could be used to tell you about temperature. However, as you can imagine, the actual processes that are involved in this are not quite as simple or as clean as the graph makes it out to be. And there's some other things that affect temperature. And so what I want to look at, or what my lab looks at, is exactly what else other than temperature is affecting these proxies, this magnesium proxy, and how can we make this proxy better so we have clearer measurements moving on to the future. And the way I actually do that is by capturing live forams and growing them in the lab in controlled conditions so that I can basically change the conditions they're living in and use that to figure out what else is affecting that proxy. And how we do that is we actually capture them with divers. So despite the fact that these guys are about 0.5 millimeter wide and barely visible with naked eye, somehow our divers are managing to catch them by hand in jars. And so the top jar has samples and the bottom are empty jars, and they actually catch them by hand. We take them back to the lab and analyze them, and here's just another picture of someone catching forams. We take them back to the lab and we grow them in these tanks. An individual foram is in each individual jar, and the water has known conditions, and all of these tanks are kept at constant temperature. And then when they die, we take their shells and analyze them, and we basically see what they've done with the conditions that we've given them. And using that, we can figure out more about how they're incorporating magnesium into their shells and what that means for our proxy. So one of the things that I personally found out is that the shape of the organism actually has a lot of impact on how the proxy comes out at the end. So we sort of knew this because we knew that the amount of magnesium in foram shells is related to the species. So different species have different ratios of magnesium to temperature. But what we did find out was that even within the same species, so these two, A and B, are the same species, but they are a slightly different shape. And they might actually have different values of magnesium. And this doesn't mean that the proxy doesn't work, but what it does mean is that if we can figure out exactly why that happens, if we can dial in on what exactly is making this organism do this, then we can take that effect out of our measurements and have nicer and cleaner climate measurements going on into the future. And so this might seem like a small thing when compared to the big issue of climate change, but science is often a lot of people working on small parts of a very big issue. And then if everyone works on different parts, we can all work together to solve the bigger problem. How are we going to adapt to climate change moving on to the future? Or how are we going to stop it in its tracks entirely? So my personal goals are basically to keep studying this, to just keep learning more about this and keep doing this. But you don't have to be a scientist at all to help with the climate change problem. And so before I leave today, I just want to leave you guys with some ways that you can reduce your carbon footprint, so the personal contribution that you're making to climate change. Drive less, because as you guys all know, our cars burn gasoline, and so that's a huge contributor to climate change. So if you can carpool, take the bus, take the bike, or walk every now and then, that actually helps with climate change. Conserve energy, because a lot of electricity is still fossil fuels. So just doing things like unplugging your cell phones when you're not using them, or turning off the lights when you leave the room, can actually really help. Cut back on meat, because meat production actually contributes a lot to climate change and produces a lot of greenhouse gases. And this is not saying become a vegetarian right now, but maybe if you have one meat-free meal a day or eat more fish or more vegetables, that would actually be very helpful. Reduce waste and get informed. Learn things about climate change. Ask questions. Go to talks like this. Go to more talks. There are a lot of resources that help you learn more about climate change, and get involved. I mean, all of these things may seem very small, but like a lot of people working together to solve one scientific problem, if everybody does some of the small things, I'm sure we can get together and solve this big problem of climate change. And I mean, we only have one planet, so we're going to have to make the best of it in the future, no matter what. Climate change is an international problem that requires an international solution. So this is actually a picture from the Conference of the Parties last year in Paris, where different countries put together an agreement where they said that they were going to keep climate change below 2 degrees Celsius. And this is great and all, but if we don't actually start working on this, this is going it's going to have this agreement is going to have a very hard time actually gaining any traction unless people start getting involved and people start working on these issues and really believing that these are an issue, that these are issues. And people have really started all over the world caring about climate change. Even the Pope has gotten in on it, and he said very succinctly, the time for seeking global solutions is running out. We can only find suitable solutions if we act together and in agreement. And he also said a quote which I love, if we destroy creation, creation will destroy us. So climate change shouldn't be a political issue, and I hate that it's become a political issue. It's something that's going to affect us all. It's going to affect human life and human society moving on into the future. It's going to affect everyone regardless of race or nationality or religion or political affiliation. And this is really a pivotal point in time in human history. History is going to look back on our generation, and they're going to look at us and ask us, ask what did we do? And I hope that when they look back at us, they're going to look back at us and say that we came together even at the last minute and changed things, instead of bickering among ourselves until it was a little too late. And so with that, I'd like to thank the Engage speaker series for letting me speak today in Town Hall, my department, my friends and family, and all of you for being here at this talk. I'll take any questions. I think we're a little over time, but these resources are some resources to help if you want to learn more about climate change. Thank you.
I assume the species that you're studying are not the same ones that you're looking at in the fossil record. So how would you apply anything you learned from today's physiological insights to your paleo record?
So actually, one of the species I'm studying actually is a species that exists in the fossil record. The other one isn't really, it exists in the fossil record. We don't use it too much for paleo oceanographic measurements because but we use it a lot in the lab because its spherical shape is a very simple geometry that lets us, it's basically our lab rat because it's so simple. But hopefully the idea is if we can figure out what's going on with that species, which is simple, we can extrapolate that and look at more complicated species. And thankfully some forams that we use in the record are still alive and still in the modern ocean today. Not all are, but the relatives are.